Okay, before we get into this, I need for you to watch that video by Mr. Johnson about the different types of solids. It perfectly encapsulates what I'm about to talk about, but has really good graphics in it because I draw like your average baboon. So it's not good for me to draw these things, but he's got stuff on there that's really good. It only lasts like 4 minutes, so if you haven't watched it yet, stop it now and go back and check that out. Okay? Now, types of solids. There are 4 types of solids that you are going to need to identify, and the periodic chart is going to help. So you really need to get your periodic charts out as we go through these discussions. Now, a lot of this is going to sound familiar because we're rehashing some stuff we've done in the past, and it helps to hear it over and over and over again in order to really become totally familiar with it. Many of you pretty much are. There's some of you still that need to keep working on this. The first type of solid I want to talk about is metallic solids. Now, metallic solids, like you've seen sheets of metal or you've seen pipes with metal, these are organized metallic pure substances. In other words, when you get a copper pipe, it is 100% copper. There's usually nothing mixed with it. Now, there are alloys out there that make it brittle, and you can shape it to where you want if you can get a mold for it. But generally, most of these substances are pure metallic. They are considered an organized group of metal atoms held together by roaming electrons. And when I say roaming electrons, we've talked about D and F electrons in electron configurations. And D and F electrons tend to move around within the atom to stabilize it. And it's a thing that if you get into heavy chemistry when you go into college, this becomes important. But trust me to say that they are able to move about, which is why a lot of these transition metals, which have D and F electrons in them, have multiple charges because of the fact of how these electrons move within the atom. But not only do they move within the atom, they're able to move across other like atoms. So like when you have a sheet of copper, the electrons that are being shared by all the coppers are being, basically the average is the same, but overall you may have overabundance of one end than another because the electrons are constantly moving, or as I say, roaming. So that's metallic bonds. Okay, so if you see a substance in which you find just the metal on here, it's like, say, copper, element number 29. That is in the metallic group over here, left of the staircase, and by itself, and that's the key, it's got to be by itself, that's going to be a metallic bond. Okay? The next one is ionic. We talked about ionic bonds a bajillion times, but just to refresh your memory, it is the combination of a group of positive ions, which is 99% of the time metals. Every once in a while, polyatomic ion like ammonium is included, but generally this is going to be positive ions with metals combined with negative ions or nonmetals or negative polyatomic ions that are attracted to form a lattice. Now, a lattice, to make sure you understand what a lattice is, if you've ever been to a house where they have these wooden structures that with these slats of wood at different angles, that's a geometric shape called a lattice. It's an organized system. These elements and compounds are really good at creating these lattices because they are very stable. Their stability allows them to exist in that form despite atmospheric pressures that may vary. Now, you get supreme pressures, and that's a different story, but normal atmospheric pressures are not going to affect these structures at all. So that's going to be a combination of positive ions, usually metals, with negative ions, which are the nonmetals or the negative polyatomic ions. Okay, molecular ones is kind of the same as the covalent, or the molecular is the covalent version of the ionic, and then instead of having positive negative ions, we have positive-like and negative-like parts of molecules in covalent structures. So it's the covalent version of ionic solid. Polar molecules are attracted to other polar molecules because positive on one side is attracted to negative, and they will create a lattice structure as well. Nonpolar molecules will also be attracted to nonpolar molecules because of their London dispersion forces, which is the instantaneous shifting of electrons from one part to another, creating these positive-like and negative-like sections throughout the molecule, and the corresponding or consecutive molecule will be doing the same kind of thing. And there's these instant attractions all across. And again, the larger the molecule, the more likely this is going to be a solid. And so the polar molecules are going to be attracted by either hydrogen or dipole-dipole bonds, because that's how that works. The hydrogen bond is the hydrogen on the oxygen, where dipole-dipole is an electronegative element with some other positive-like area. Nonpolar is, like I said, is completely nonpolar, but they are attracted by the instantaneous change of electrons. And the last one is the covalent network. Now this is a really interesting one. Covalent network is basically the non-metal version of metallic bonds. And a good example of this is carbon. Carbon has all kinds of shapes that, when they are bonded together, they can create different, what we call allotropes. Allotropes are the same structure or same substance but different structures. And so what happens is that instead of the D and F electrons that hold the ionic or the metallic atoms together, the valence electrons, the outermost electrons, which for nonmetals is usually 6, 7, that area carbon is 4, they create bonds because of that. And a lot of the amorphous solids that were talked about in his video, Mr. Johnson's video, are made of non-metal networks, so, or as we call covalent networks. But also the complex geometric structures are found as well, and this is where carbon comes into play. Now, did you know that diamond and graphite are made of the same material? It's pure carbon. Diamond is pure carbon. It's just that it's been pressurized to the point where the geometric structure is really, really solid. I mean that from both meanings of the term. This is why it's considered the hardest mineral out there. It will scratch all other surfaces because that structure is so stable. It will do that. However, graphite, which is exactly the same material, but it's geometrically shaped in layers, and then the layers are held together by the London dispersion forces. But because the London dispersion forces are so weak, particularly in that structure where there's no support geometrically, it's all laid out and then these weak bonds holding the layers together. This is why graphite is really good for pencils, because when you write, it actually slips off of the pencil onto your surface and you can read the result. Or it's also really good as a lubricant. If you have a frozen lock in the middle of winter, probably your best chance is not to pour hot water on it, but to squirt some of this stuff in there. Just solid. It's not going to freeze up because it's already frozen, but now it's going to be able to lubricate the mechanism to unlock your car. Another one that is also carbon is Buckminster fullerenes. Buckminster fullerenes are 60 carbon plus groups that form shapes that look like geodesic domes. Now, if you've never seen a geodesic dome, I've got a structure on there. All these structures are represented, I have shown, I've got pictures of in your Google Classroom. Take a look at it so you can see how they differ. Okay? So, your practice problem can be about classifying these types of materials. So, as to what kind of solid each of these become. So sodium is a metal over here, so we know that this is going to be metallic. Now water, you say, well, wait a minute, water is a liquid. No, but you know water becomes a solid, and because it's a solid, it becomes then incumbent upon us to figure out what this is going to be. And this is going to be, as what we call over here, the molecular bond, because it is a polar molecule. Okay? So, this is going to be molecular. And This is why when you add a solute to water and you want to freeze it, it takes longer to freeze because it has to get into this geometric structure to form ice, and these solute particles get in the way of it. So that's why the freezing point of water lowers, because it takes longer to get to that structure. The next one is what we call the covalent network, because boron is a nonmetal, it's over here, although it's in the metalloid section, but it is considered as well as a nonmetal. It's on that right side there. So this is the covalent network, a lot like carbon. And then sodium chloride. There's a metal combined with a nonmetal that, as we've seen a bajillion times, is ionic. So that's what we're doing with this. So go ahead and go to your practice problems. Look at the video that Mr. Johnson did. If you're not done, you really need to look at this so you can see what I'm talking about here. And look at those pictures of the different structures to get an idea of what I'm talking about. All right? Do those practice problems and, of course, have fun.